Hello everyone, welcome you all for the post-contest discussion of Leetcode Weekly 409. So let's start with the discussion. The first problem for the day is design neighbor sum service. So the question reads as you are given an n cross n 2D array grid containing distinct elements in the range 0 to n square minus 1. Okay. You need to implement the neighbor sum class where neighbor sum int you have three functions in it where a neighbor sum this is something that initializes the object. Int adjacent sum int value returns the sum of elements which are adjacent neighbors of value, that is either to the top, left, right, or bottom of value in grid. And int diagonal sum int value is a function that returns the sum of elements which are diagonal neighbors of value, that is either to the top left, top right, bottom left, or bottom right of value in the grid. So like as for example, you can see you have been given a grid something like this. And first of all, you initialize the object, then you call the adjacent sum. Like for example, if you observe, yeah. So then you call the adjacent sum on the adjacent sum for 1. So if you look, the adjacent sum for 1 are 0, the adjacent numbers are 0, 2, and 4. So if you simply add them, the result would be 6 and you are returning 6. Similarly, again, you are calling the adjacent sum for 4, for value 4. So what is the adjacent sum for value 4? So if you look up for 4, what are the adjacent values? They are 1, 3, 5, and 7. So if you simply add them up, you will get 16. Then you are calling diagonal sum for 4. So if you call diagonal sum for 4, so what are the diagonal elements for 4? They are 2, 0, 6, and 8. So if you simply sum them down, you will get 16 again. And then again you are calling diagonal sum for value 8. And the diagonal sum for value 8, the only diagonal element for 8 is 4. So the answer will be 4. So this is something that you need to do. So you have the neighbor. So let's understand what we need to do. So you have a grid, you have a grid, and it is given to you that these grid contains all the distinct elements. So if this is an n cross n grid, so how many values should it contain for all the elements to be distinct? N square values, isn't it? And it is given to you that this grid contains values from 0 to n square minus 1. All values are distinct. Now, every time what you are doing, if you are calling an adjacent sum function with some value, you need to return the sum of values that are the adjacent to a particular element. So let's suppose I want the adjacent values, like since all values are distinct, so this particular value will be present at a particular cell, at single cell, isn't it? At some single cell. So let's suppose this particular value is present at this particular cell. So if I am calling the adjacent function with this particular value, what should I return? I should return sum of this element, and this element, isn't it? So can I say that if I am standing at I comma j, if I am standing at any I comma j, so its possible adjacent elements are I minus 1 comma j, I j minus 1, I j plus 1, and I plus 1 comma j. So these are the possible adjacent elements that an element standing at I comma j has. So what I need to do, I first of all need to find out this I comma j for that particular value. If I am able to do that, so I will just simply check that these adjacent elements exist or not. Like for example, if your value is this, do I minus 1 comma j exist? Do I minus 1 comma j exist? The answer is no. I minus 1 comma j does not exist. You can see, isn't it? And how will we get this? If when we do I minus 1, it will become lesser than 0. Can index lesser than 0 can exist? No. So this is how we can check that whether the top value exists or not. Similarly, for checking if the left adjacent element exists or not, what we will check? We will simply check if j minus 1 is greater than equals to 0 or not. If it is not so, then we know that j minus 1 does not exist. Similarly, for checking that down adjacent element exists or not. So what we will do? We will simply check that whether I plus 1 is lesser than n or not. If it is lesser than n, then the element towards the adjacent down element exists. Otherwise, it does not exist. And similarly, for checking the adjacent element towards the right, I will simply check that if j plus 1 is lesser than n or not. If it is, then it exists. Otherwise, it does not exist. This is how I can see that whether the adjacent element exists or not. And if it exists, we can take the sum. Similarly, when we talk of diagonal elements of I comma j, we have to implement two functions, adjacent sum and diagonal sum. Diagonal sum for a particular value. So if we have a particular value, let's suppose its index in the grid is I comma j. So what are its diagonal elements? Its diagonal elements are I minus 1 comma j minus 1, I plus 1 comma j minus 1, I minus 1 comma j plus 1, and I plus 1 comma j plus 1. These are its diagonal elements. So similarly, as we did in adjacent sum, checking that whether this exists or not, this exists or not, this exists or not, or this exists or not. Similarly, by doing that, we can check that whether these diagonal elements exist or not. And if it exists, we can just simply add the sum for each of these values and at the end return the sum. That's a simple, straightforward logic for this question. So let's understand it via the code. So first of all, we were given this neighbor sum vector of vector int ampersand greet. This is something like a constructor. This is a constructor. So what we did is we kept two things: the integer value n, that is the size of the greet, and this vector v of size n. Once we get a greet, what we will do, we will make this v equals to grid. So for that, what we did is we initialized our n with the size of the grid, because now we know that the grid that we are going to use is of n cross n, and the value of n is equals to grid dot size. And we resized our vector v with a 2D matrix n cross n. So this is how we can do, like if we let's suppose have a vector v and we want to make a 2D vector of size n cross n, make this v as a 2D vector of size n cross n. So this is something that you can write. If someone don't know, this is something that we can resize the vector. So v dot resize n, this is for number of rows, comma, every column is of type vector int and of size n. And going to each and every element, we simply did v of I of j is equals to grid of I of j. So this is how we made v equals to grid. Once we implemented this thing, let's come to adjacent sum function. So adjacent sum function has the value of whose adjacent elements we need to find, initialized our answer to 0, went to each and every cell. The cell at which we find that, okay, if v of I of j is equal to value, if we find that, so what we did, we first of all initialized our answer to 0. We can just neglect this answer as of now. It's not needed. So we initialized our answer to 0. If I minus 1 is greater than equals to 0, so what do it means? It means that we have the adjacent element towards the top, isn't it? So added that to our answer. Similarly, if I plus 1 is lesser than n, so we know that we have the adjacent element towards the down. So added that to our answer. Similarly, for the left adjacent element and for the right adjacent element. And once we are done with this, we simply returned the answer. Okay. So this is how we implemented the adjacent sum function. The same way we have implemented the diagonal sum function as well. Going to each and every cell. If we find a cell that is equal to this value, so we are initializing our answer to 0. And similarly, that if I minus 1 is lesser than 0, that is, if I minus 1 is lesser than equals to 0, then there are two possibilities, that this can also exist and this can also exist. So if j minus 1 is greater than equals to 0, this means that this particular diagonal element exists. This particular diagonal element exists. So adding that to our answer. Similarly, if j plus 1 is less than n, this means that this diagonal element exists. So adding that to our answer. And similarly for the other two diagonal elements as well. Once we are done with this, we are returning our answer. So this was a pretty straightforward question. We only need to go to that particular value cell and just check for its adjacent elements and diagonal elements. Once you're done with this, you are good to go. Okay. So let's see how we can solve the second question. So for the prerequisite for solving the second question will be, you should know the shortest path algorithm from a source to all the nodes. That is the Dijkstra algorithm. If anyone is not familiar with that, I would first recommend that first of all, just give a quick check on that. learn that, and then you can solve this question. So the name of the question is shortest distance after road addition queries 1. So you are given an integer n and a 2D integer array queries. There are n cities numbered from 0 to n minus 1. Initially, there is a unidirectional road from city I to city I plus 1. Now, queries of I is of the form ui, comma vi represents the addition of new unidirectional road from city ui to city vi. After each query, you need to find the length of the shortest path from city 0 to city n minus 1. Return an answer where for each I in the range 0 to queries.length minus 1, queries of I is the length of the shortest path from city 0 to city n minus 1 after processing first I plus 1 queries. Okay. So the main thing for this question was that n was given of the order of 500. And when you see this that n is order of 500, the first thing that will come to our mind that we can use that extra y. See, let's understand the question once again first. So initially what you are given is you are given nodes 0, 1, 2, 3, 4. Let's suppose the value of n is 6. So you have nodes from 0 to 5. And initially you have a unidirectional road between I and I plus 1. That is from 0 you can go to 1. From 1 you can go to 2. From 2 you can go to 3. From 3 you can go to 4. And for 4 you can go to 5. Initially this is given. Now what they have given you is they have given you a queries vector. Okay. So in every query, they have given you some ui, comma vi. This means that at this particular point of time, when you are handling this particular query, you are adding an edge between node ui and vi. So let's suppose I have a query something like this, 0, I have a query something like this, 1, comma 4. So what does this mean? This means that I added an edge from 1 to 4, a unidirectional edge from 1 to 4. What do we mean by unidirectional? Unidirectional means that we can go from 1 to 4, but we can't come from 4 to 1. Okay. So yeah, we can go from 1 to 4. So now just check. If we can go from 1 to 4, what will be the shortest distance from 0 to 5? What will be the shortest distance from 0 to 5? It will be, you will go from 0 to 1, then 1 to 4, and then 4 to 5. So the shortest distance between 0 to 5 is changed to 3, whereas earlier it was, if this edge was not present, so the earlier distance was 5. Isn't it? The earlier distance was 5, now it has changed to 3. Similarly, you will be given many such queries, and after every query, you need to tell that what is the shortest distance from 0 to 5. So first of all, what we got? We got the word shortest distance. So we know that we have an algorithm to find the shortest distance from a source node to the target node. We have an algorithm for that. Okay. But can we apply that algorithm over here? Will we get TLE? Let's check. So we know that we have queries of the order of, if you observe, we have queries of the order of 500. That is, we have at max 500 queries. Okay. What is the time complexity of Dijkstra shortest path algorithm? It is something like n log e plus log b, something like this. V into log e plus log b. So we can say that it will be somewhere around 500 into 500 multiplied by log of 500, something like this, isn't it? So this will definitely pass our test cases. So that's the reason we can directly apply Dijkstra in this particular algorithm. So again, I would repeat that the ones who don't know the Dijkstra, I would highly recommend you that first of all you watch that so that the things become clear and the intuition becomes clear that why we are going to use Dijkstra for this question, because we have a direct algorithm for finding the shortest path. The only question was that can we apply it over here or not, because the question that comes to our mind is that will it give TLE? So we have checked that since it will not give TLE, we can directly say that we can apply Dijkstra over here. So let's look to the code. It's actually a direct implementation. We don't have any more logic over here. So let's jump onto the code. So what I did is, we don't need this temp. Okay. So I constructed an adjacency vector of size n and initialized my m with the size of the queries. Now I know that initially what I have. Initially, I have an edge from between I and I plus 1 till I equals to n minus 2, isn't it? So I went to each and every I from 0 to n minus 2, and in my adjacency of I pushed back I plus 1. That is, I have an edge from I to I plus 1. Then initialized my vector int answer m with size m. Then I went to each and every query, took the starting point in start, ending point in end, and we know that since we have an edge from start to end, so in adjacency of start, I simply pushed back end. Then a simple Dijkstra algorithm code. Let me go through it quickly. So we have the distance vector of size n, initialize it with some maximum distance, initialized my distance of 0 with 0, then made a priority queue as we do in Dijkstra algorithm, that the first value of the pair will contain node and the second will contain its distance. Then in my priority queue, I simply pushed back 0, 0. That is, initially I am standing at node 0, and to reach that particular node, my distance is 0. Now, while my priority queue is not empty, first of all, took the topmost element of priority queue and popped from the priority queue. Then I know that node value is the first value of the pair and the distance is the second value. Now, if distance vector, if in the distance vector, this particular node has a lesser distance, as we have got the distance now, so we know that this particular node is reachable at some lesser distance in comparison to what we have now. So in that case, we are simply continuing. We are not moving forward with this particular node. But if it is not so, we are going to each and every adjacency node of this particular node. And if the adjacent node have a distance greater than the distance we require to reach this particular node plus 1, so in that case, we know that this particular node IT can be reached in distance d plus 1, but it has some greater distance. So we will update this distance, and in our priority queue, simply push this particular node and its distance. It's a simple implementation of Dijkstra. So once we are done with this, so we know now distance of n minus 1 contains the shortest distance from our source node 0 to n minus 1. So our answer of I will become distance of n minus 1. And at the end, we are returning our answer vector. So that was the simple code for the second question. So let's jump on to the third question for the day, and it had something in it. It was not like the second one. Let's see why, and let's understand it. So the name of the question is shortest distance after road addition queries 2. So you are given an integer n and a 2D integer queries. There are n cities numbered from 0 to n minus 1. Initially, there is a unidirectional road from city I to city I plus 1. So queries of I is ui comma vi represent the addition of new unidirectional road from city ui to city vi. After each query, you need to find the length of the shortest path from city 0 to city n minus 1. So the question till here remains the same as the second question. Till here, it remains the same as the second question, but from here, this particular line makes this particular question different. This line is also same. Like for every query, you need to return the answer. Like till that particular point, if we add the edge, so what will be the like shortest distance from 0 to n minus 1? So the question remains the same, but we have an additional point over here, additional line over here. And because of this line, we also have the value of n increased. Now, in the second question, the value of n was of the order of 500, but in this particular question, it is of the order of 10 power 5. So how we can do this? First of all, let's understand what's written in this particular line. So it's written that there are no two queries such that queries of I of 0 is lesser than queries of j of 0, is lesser than queries of I of 1, is lesser than queries of j of 1. What does this mean? If you were able to decode this particular point, then the question was a bit solvable. Let's see how. So it's given to you that you don't have any two queries such that if let's suppose for a particular query says that we can reach this particular node to this particular node. This is some ith query and it tells me that from this particular node you can reach this particular node. Now there is some other query. If that another query tells you that you are starting from this particular node, you have an edge from start to end. You have an edge from start to end. And if your start is somewhere over here, if your start is somewhere over here, so your end cannot be something like this. You can't have an edge something like this from this node to this node, because it's mentioned that if queries of I of 0, you don't have something like this, that queries of I of 0, that is for ith node, the start query is lesser than queries of j of 0, that is for the jth query, the starting node, is lesser than queries of I of 1, that is the end node for queries of I, is lesser than queries of j of 1. The case that we have drawn matches to this particular statement. And we know that in the question it is given that we don't have any queries I comma j like this. So what are the possibilities? What are the possibilities? The possibilities are that if you have an edge from this particular node to this particular node, and now, if you have an edge from this particular node, then it will end somewhere over here. We will have an edge something like this, or this, or this. At max, it can go till here. It can't cross this particular node, isn't it? So now, just try to imagine. You can even have something like this. That if initially you have a node something like this, so again you will not have something like this as well. That you are starting from here and you are ending at here. You will not have something like this as well, because again it forms the same case. So if let's suppose if you already had an edge, this particular edge, then if you have the starting node of another query something over here, so what are the possible edges it will have? It will have either something like this, either something like this, either something like this, or something like this. These are the possibilities it will have, isn't it? Okay. Now just try to imagine, now just try to think one thing. That okay, if we have an edge, if we have one node over here and one node over here for one particular query. Now in the next query, in some forward query, I tell you that I have an edge something like this. So just try to think, will it reduce the shortest distance from 0 to n minus 1? Let me explain it by this. You have nodes something like this. Okay. And let's suppose you already have an edge something like this from 2 to 4. Oh, let's not take from 2 to 4. Let's take from 1 to 4. If I tell you that I have an edge something like this, now just tell me if I have an edge something like this, what's the shortest distance from 0 to 5? It is 0 to 1, then 1 to 4, and then 4 to 5. So the shortest distance is 3. Now if I say you that I have an edge from 2 to 3, will the shortest distance be affected? Will the shortest distance be affected? The answer is no, because it's a common sense. Like the shortest distance will not be affected because this edge helps you to go from 2 to 3, and we already have an edge from 1 to 4, so you will prefer this particular edge, right? Similarly, if I have an edge something like this, will the shortest distance be affected? The answer is again no. Okay. If I have an edge something like this, let's suppose I have an one thing that is very much clear is that if we have an edge something like this and we are starting at some nodes in between these nodes, so if our starting node for any of the query is between like 2 or 3, so we know that these are something that we should not take, because even if we are starting at 3, the maximum that we can go is 4, because of that statement that was given, because of this particular statement. We can't cross 4. And we know that we already have an edge from 1 to 4, so this particular edge is of no use to us. So if we have an edge between 1 to 4, the use of this node 2 and node 3 is not anymore. We can simply delete these particular nodes. We will not delete in our code, but just for imagining what we can say that we can delete this particular node. But just try to think, can we delete 1? Or can we say that 1 is of no use to us? The answer is no. Why? Because we can have an new, in some other query, we can have an edge something like this. If you have an edge something like this, now you just observe the shortest distance from 0 to 5 becomes 2. So it's always that only the middle nodes will get deleted and not any other nodes. Okay, only middle nodes will of no use to us. So now how to write the code for this? Because the main part in this question was the implementation. So if I let's suppose have nodes like this 0, 1, 2, 3, 4, 5, 6, 7. And if let's suppose I have an edge something like this, that I am able to go from 5 to 6, I am able to go from 4 to 6, I am able to go from 3 to 4. And now what I do is I add an edge from 1 to 3. Like this was the earlier case. Okay, this was the earlier case. And now what I am doing is, so first of all, what is the earlier distance? If I tell you, if I store the shortest distance till now in temp, so what is the distance? What is that distance? If you observe, it is 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay, so you have the shortest distance as 6. Now, if I tell you that I am adding an edge from, let's suppose 1 to 3, and I just put a simple question in front of you that now tell me by how much distance my temp will get reduced. First of all, one thing that you all need to understand is that if let's suppose I already have node sequence something like this, and I already have an edge something like this, and I am putting forward a new edge something like this, so this edge is of no use to us. Like this edge will not reduce any of the distance, isn't it? Okay. So this thing should be clear. If this thing is clear, now just I tell you that I have an edge something like this, and just tell me what is the shortest, but how much distance will get reduced from 0 to 7 if we are talking of the shortest distance. Before coming to that, what I would say is, see, observe one thing. Since you have an edge from 3 to 4, so all nodes that are in between 3 to 4 are of no use to us now. They are to be deleted, right? So we will maintain some map. What I did is I maintained a map, and all the middle nodes in that map I marked as true. So I don't have any nodes from 3 to 4, so no use to us. Similarly, if we have an edge from 4 to 6, and in between we have a node 5. So we will mark MP of 5 as true. That is, this node 5 is of now no use to us. Okay. Now I know my shortest distance till now is 6, and I have added a new edge from 1 to 3. So let's observe what will be the, by how much distance my shortest distance will get reduced. So before 1, since I added an edge from 1 to 3, just tell me, will the shortest distance before 1 will get affected? Will it get affected? The answer is no. So it will start get affecting from 1, isn't it? So first of all, we are standing at 1. So all the starting distance before 1 will not be affected. Okay, we have an edge from 3 to 4, 4 to 6, and 5 to 6. So what I did is I maintained a vector for every index. I maintained a vector like for this, I will have a vector of size 8 for index 0, 1, 2, 3, 4, 5, 6, 7, and initialized all values to -1. Now, whenever I have an edge, let's suppose from 3 to 4, so what I will do is in the index 3, I will simply write 4. That is, from 3, I can go to 4. I have an edge from 4 to 6. In my index 4, I will simply write 6. Similarly, I have an edge from 5 to 6. In my index 5, I will write 6. So this is how vector v looks for me as of now. Now I am adding an edge from 1 to 3. So I will try to see that by how much my shortest distance will get reduced. So what I will do, I will just start traversing from 1 and just check that if I am going from 1 to 3, like what is happening? Just imagine. I am going from this start to end. So earlier I was taking 2 edges to go from 1 to 3, but now that the job will be done in 1. So my shortest distance should get reduced by 1, isn't it? So what I will do is I will start from 1 and just check that till reaching 3, what is the number of edges that I need to traverse. I repeat, I start at 1 and check edges needed to reach 3. In this question, in this example, you can see if I start from 1, the edges that I require to reach 3, the edges that I require to reach 3 is, number of edges that I require to reach 3 is 2. And I can do that in 1. I can do that in 1. So what I will do is, I will reduce my temp with 1. So my temp will now become 5. And this will be my shortest distance for this particular query. If I let's suppose had something like this, if I let's suppose had something like this, that I am starting from 1 and I am going till 7. Starting from 1, you can't go till 5, isn't it? Because of that particular constraint in the question that was mentioned, that particular line. So if let's suppose starting from 1, you are going till 7. So just check that if you start at 1 and want to go till 7, what is the shortest distance that you require? So if I just try to see what is the shortest distance that I require, so I am starting at 1. So I will go to 2. Yeah, I can go to 2. So it will take me an edge 1. From 2, I will go to 3. Yeah, again. So it will take me an edge 1 again. From 3, I will go to 4. It will take me an edge 1 again. From 4, I will go to 6. How I am getting to know that from 4 I can go to 6 or not? By looking at this B vector. If the value at 4 is not equals to -1, this means that from 4 I can go to 6, isn't it? So it will again plus 1, and from 6 to 7 it is again plus 1. So 1 plus 1 plus 1 plus 1 plus 1. So as of now, the shortest distance, the distance from 1 to 7 is 5. But I know that I have a new edge that will help me to reach from 1 to 7 in by only a 1 edge. That is by only 1 distance. So by how much my temp will get reduced now? Earlier it was 6. Earlier it was 6. So I know that earlier distance from 1 to 7 was 5, but now I can do that in 1. So my temp will get reduced by 4. So wait a minute. So yeah. So if I just reduce it by 4, so 6 will become 6 minus 4, that is equals to 2. And you can check that the shortest distance from 0 to 7 is 2 only, from 0 to 1 and from 1 to 7. So this is how you will solve the question. This is how you will solve the question. At every point of time, you will check that if you are adding a new edge from some start to some end. So first of all, you will calculate that what is the shortest distance as of now. And if that shortest distance is lesser than what actually it takes, like let's suppose the shortest distance was 1 only. That initially also from 1 to 7 we required 1 only, and now also we are requiring 1 only. So there is no point on making that statement, isn't it? So if the shortest distance as of now is lesser, so we will just reduce the value of this temp and just print the answer. So that's the logic for this particular question. Let me show you all the implementation. So what I did is, I know that the initial shortest distance from 0 to node n-1 is n-1, isn't it? Then for the 0th query, I just found out what is written at the start of the 0th query, what is the start node and what is the end node. So just tell me by how much my temp will get reduced. Like if I have a node from 0, I have something like this. And initially I have an edge from 1 to 3. So by how much my shortest distance got reduced? It got reduced by 3 minus 1 minus 1, isn't it? For the first edge, it got reduced by 3 minus 1 minus 1. That is end minus start minus 1. So temp got reduced by end, that is maxi, minus start, that is mini, minus 1. Then I constructed a vector v of size n and initialized it to -1. This is the same vector that I was talking over here. That from any node 0, what is the node that I can reach? Okay. So, and what I did is I kept a map. What is this map doing? Map is just if I know that I have an edge from 1 to 6. So I know that nodes 2, 3, 4, and 5 are of no use to us now. That if we are starting from these particular nodes, we don't need to handle this particular case. So what I am doing is, for this particular values in my map, I will mark them true. So this is something that map help us, that if we have a query for which the starting node is something that has the value in map marked as true, this means that we don't need that particular query is of no use to us, and we can simply continue from there, because it will not help to reduce the shortest distance anymore, isn't it? So we can continue from there. So that where map help us. And we know that from the start node, we will be able to reach the end node for the first query. So in our V of mini, we simply mark the value as maxi, that is the end node. And we went to each nodes in between mini and maxi, that is we started from mini plus 1 and less than maxi, I plus plus. We simply marked that particular node as true. Okay. Then the size of the queries we took in M and initialized our answer with size M. And we know that for the first query, the answer is stored in temp. Now for every query, we will see that how much distance we can reduce. That is something that we will check. So we went to each and every query. Now, if mp.find queries of I of 0 is not equals to mp.end, that is our starting node is something that is no use of us. So we know that this particular query or this particular edge will not help us to reduce the shortest distance, and hence the answer will remain the same. So we just kept answer of I as temp. If this is not the case, we initialized our start with the start node and end with queries of I of 1 and initialized our count to 0. This count will be something that will tell me by how much my shortest distance will get reduced. So it will tell me that as of now, this count will tell me that what is the shortest distance from start to end if we are not adding this ith query. If we are not adding this ith query. So if we add that ith query, by how much the shortest distance will get reduced? Count minus 1. Like if from 1 to 5, initially we have the shortest distance as 4. And if we add an edge from 1 to 5, so the distance will become 1. So by how much the distance got reduced? Distance got reduced by 4 minus 1. The shortest distance got reduced by 4 minus 1. So this count tells me that if I am not adding that ith edge, so what is the shortest distance from start to end? Okay. So initialize my j to start while j is lesser than end. If v of j is not equals to minus 1, what does this mean? This means if v of j is not equals to minus 1, like if we have an s something like this, our j is something over here, and v of j is not equals to minus 1, this means that from j we can reach to some nodes, isn't it? From j we can reach to some node. Now, just imagine, this is the start node, let's suppose, okay? Let's suppose we have something like this. This is the start node. And initially we have the edge something like this. This is our current end node. That is, we are trying to add an edge between this node and this node. This is something that we are trying to do. So our j is initially over here. So I know that my v of j is not equals to minus 1. So from this particular node, when I try to find the shortest distance from this node to this node, when I am not adding this edge, so from here I will go over here. From here I will go over there, here. But just tell me, should I remove this particular node? By removing, I mean marking it true in my map. So should I remove this particular node? The answer is no. I will not remove this particular node because I know that this is my start node. All the nodes from between start to end, all the nodes between start to end gets deleted. Like for example, if I have the case something like this, that is I have an edge between this to this, and this is my start node and this is my end node. That is, I am trying to add an edge between this and this. So now when my j comes over here, and I go from here to here, so I should mark this as true in my map, because now this particular node is a middle node for this particular edge. This particular node will become the middle node for this particular edge. So when I will mark this particular node as true, only when this particular node is not the start node. So if v of j is not equals to minus 1, then very good. We will jump to some nodes, but before jumping, we need to mark this jth node as true only when j is not equals to start. So if j is not equals to start, we simply marked it as true in my map, And now I know that now what my j will become. If this is 1 and this is 3, so now my j, if j is initially 1, so it will now become 3. It will become 3. So since after this if else statement, I was doing an extra j plus plus. So over here, what I did is I marked j as vj minus 1. Ultimately, after j plus plus, it will become vj. Okay. And incremented my count that, okay, I have an additional edge from j to vj. And else, if this was not the case, that is v of j was not equals to minus 1, v of j was equals to minus 1, that is from this particular node, I don't have any jump node. I will simply move to the adjacent node. So what I will do, I will simply mark j as true if j is not equals to start and simply increment my count. Now at the end, I know that from start to end, I need to traverse count number of edges, but I have a node, I have an edge in this particular query, which will help me to traverse from start to end in in only one distance. So by how much my shortest distance temp will get reduced, it will get reduced by count minus 1. And now I know that I have an edge from start to end, that is from start, I can reach to end. So in my V of start, I simply marked as end. And I know that after processing this query, I simply did answer of I is equals to temp. That is still now, whatever edges I have, temp is the shortest distance from 0 to n minus 1. So simply marked answer of I as temp and at the end returned my answer. So this is the code for this question. I hope the logic is clear. The simple thing to understand was that if we have an edge from this particular node to this particular node, then if we are having any starting node for some other queries somewhere in between this, so they are of no use to us, because at max they can go till their end will be at max till this point, and I already have an edge from this node to this node. So these edges will not help me to reduce the shortest distance. So yeah, that's the simple implementation for the third question.